this is definitely something where I do expect that everybody will be able to get it. It just takes a little bit of time. So there's other times where I teach something like only a third of you are going to get it. But okay, so our first three lessons, we talked about limits that approach infinity. We talked about the mean value theorem. We talked about absolute min-maxes, critical numbers. They all really lead up to be able to do kind of these two main lessons. And it goes with derivative testing and then sketching curves. So we're going to kind of show you how it pieces together today. It's really, really, really foundational for calculus. So if there were, say, 6 lessons that you had to teach for calculus during the course of the year, you could only choose 6. This would make it into the top 6, okay? Chain rule would be another one, right? Pretty important deal, right? Like just derivatives with product and quotient stuff, another pretty important one. This would be one of those that you put in there, okay? One of the top 6 most important lessons. So here we go. We have a function, okay? Is the function increasing or decreasing right here? How about here? How about here? So you try to make the conjecture for me, okay? The function is increasing when the derivative is positive. Very good. So therefore, we use a derivative test. When we find out that f prime of x is greater than 0 when it's positive, the function is increasing. Decreasing when f prime of x is okay. Let's talk about mins and max. What do you notice about the derivative here? So a local min or a local max happen when we would like to say that, wouldn't we? But the fact is, it's not the case. Aaliyah, you said it's not always that situation. Can you think of a function where the derivative is 0, but yet there's not a local max or local min? We're going to give credit to Carter here that there's a cubic. I drew it exaggerated. Well, that's really bad. Okay, so everybody okay with a cubic like that? You take the derivative right at that spot, you're going to get 0 for a derivative, but yet is it a local min or a local max? No, because am I increasing or decreasing right here? And increasing here, right? So the way that we define a local max or local min is this. We have a local max when the derivative changes from positive to negative. So when the derivative changes from positive to negative, or the function changes from increasing to decreasing, that's when you have a local max. So then what will the local min be? Now, when you look at this, if it changes from positive to negative, it's got to cross over 0 by the intermediate value theorem, right? But just because it's equal to 0 doesn't necessarily mean there's a local max or local min. So we have to see a change of sign. That's critical, which I think I taught that incorrectly for about 3 years. So I always used to say, well, whatever, doesn't matter. All right, now let's get to the challenging part, okay? Let's look at second derivative. Second derivative is the rate of change of the first derivative. So, first derivative, positive or negative? What's happening to the first derivative? Yeah, it actually crossed over 0 and is becoming more negative, right? The first derivative is decreasing, right? Like the first derivative went from a positive value all of a sudden now to a negative value. Right here, is it going to become more negative or less negative? Even more negative, right? How about right here? More negative or less negative? Even more negative. Then what happens after that? More negative or less negative? Less negative. How about here? More negative or less negative? And then it changes over to, do you see what's happening with that first derivative? It's tilting down, and then finally it hits the spot where it tilts the most, and and then starts to tilt back up, right? We call that point, okay, the second derivative, f double prime, it changed from negative to positive. We call that the point of inflection, where f double prime of x changes from negative to positive, or f double prime of x changes from positive to negative. So when the second derivative changes sign, we call that the inflection point. And you guys said that happened. Well, tell me about where you feel like it happened. Right about there? Right about somewhere around there? We call that the point of inflection, and that's where concavity changes. Now, concavity is something that's new to you. Concavity is we'll define it in a second in terms of the derivative, but kind of a layman's term, we would say if you were to dump water on top of this function, would it shed water or hold water? So if I dumped it right here, would it shed water or hold water? It would shed water. So we say that it's concave down. If I dumped water right here, would it shed water or hold water? Hold water, so we say right here it's concave up. Okay? In other words, think about this. Was the first derivative decreasing or increasing here? It was decreasing, right? It was becoming more negative. So it's concave down where f double prime of x is negative. And then here, you can see that you are, that the second derivative is becoming positive again, right? So the second derivative, the first derivative is increasing. So f double prime of x is greater than 0. So the first derivative was becoming more positive again. I mixed that up the first time I said it, sorry. All right, last piece, local max or local min? Local max. Is it concave up or concave down? So a local max happens when it is concave down and the first derivative is equal to 0. So if you get a first derivative equal to 0 and it happens to be concave down at that spot, then it's a local max. If f double prime of x is greater than 0, if it's concave up and the derivative is equal to 0, then we know we're going to have a local min. Now, I like to mark these out with number lines, okay? And you don't have to write this down, but just kind of give you an idea. This is about where the first derivative is equal to 0, and right about where the first derivative is equal to 0 as well. So you would get positive here, negative here, and positive here. Because you can see that it's increasing, it's on its way up, decreasing, on its way down, and increasing on its way up. And then you have this other spot where you had inflection. You can see it's concave down, so the second derivative is negative, and the second derivative is positive. So I like to do an f double prime number line and an f prime number line in order to organize my work. And that's how it relates to the graph. Yep. Now we're going to take baby steps at first, but I'd say the first two problems we do, those should be kind of very straightforward. You want to really be able to let those sink in and fully understand them, okay? We're going to get through A, B, and C today. So, directions, there's a lot to it. It says identify intervals of increasing, decreasing, concave up, concave down, also local max, local min, and inflection points. We have a lot of stuff to do. So we're going to start with f prime of x. What's the derivative? X squared minus 4. Great. Can we figure out where that's equal to 0? Yeah, we can. Where's it equal to 0? Negative 2 and positive 2. here's where you have choice. You're going to get to do whatever you want to do in this scenario. I know what I like to do. I like to be quicker, more efficient. Okay, but we need to test to see whether or not it's positive or negative here. So what would be a number you'd plug in? So if you plug in -3, you would get -3 plus 2 is 8, negative, and -3 minus 2 is 8, negative, and a negative times a negative is 8. Okay, see how you interval test? I got a quicker way. You want to see the quicker way? What graph does that make? Right side up or upside down? Positive or negative? Done. So if you know what the graph looks like, use that to your advantage. You see that? So my first derivative test is done. I will just need to answer the question then in a second. Let's do the second derivative. F double prime of x. I get 2x. Where is that equal to 0? Do you know what that graph looks like? Negative and positive. Everybody okay with that? Okay, so then let's answer questions about increasing and decreasing. Increasing, do I look at first derivative or second derivative? First derivative. Increasing from? Union with? Decreasing? Good. I can also determine local max and local min. We're going to do that in a second. We're not going to do it right now. We're going to go over to, go get some brain food. Come back smarter. Good day. Okay, local max happens when the first derivative changes from what to what? From positive to negative. So when does it change from positive to negative? Now, this is not an interval. This is an actual coordinate. So we're going to determine the y-coordinate here in a second. The local min happens where the first derivative changes from negative to positive, which is going to be a positive 2. So how do you think I come up with the y value? Plug it into what? Yeah, plug it into the original. So if I go 1 divided by 3, x cubed minus 4x plus 2. I go to my table and I type in -2 and positive 2. You can see I get negative 7.3 repeating. Whoops, sorry. Okay, so I've got those. Now it's time to do intervals of concavity. Whoops, sorry. Yeah, no kidding. Maybe I should have to pay $1 to everybody in the classroom every time I make a mistake. Yeah, and then you guys, every time you make a mistake, you pay me $1. I'm game if you guys want to roll. All right. Okay, concavity. When is it concave up? When the second derivative is? When it's positive. So that's going to be from 0 to infinity. When is it concave down? And then my last piece is to identify the point of inflection. Inflection occurs when the second derivative changes sign, and that is at 0. If I plug 0 in, I get 2. What? Yeah, you plug 0 into the original equation. Okay. All right. So this is an actual coordinate. Intervals are for increasing, decreasing, concavity up, and concave down. The local max, local min, inflection, those are points. And we'll actually plot them for letter B here in a second. Okay. All right. Let me get rid of this. Letter B. First derivative. Does that factor? Take out a negative 4x and you get? So negative 4x times x plus 1 times x minus 1. What if it didn't factor? What would you do? Quadratic formula, very good. What are the zeros? Now, again, this is where you have choice. And some of you remember this better than others. And I'm sorry if it doesn't work out for you. I really do apologize. But I know what this cubic looks like. Is it finish going down or finish going up? Down. Why? This is negative, and it's cubic, so it's going to start opposite where it finishes, right? And it passes through 0, negative 1, and positive 1. So I know the shape of this cubic. If you don't know that, then you're going to have to do interval testing. It's just the way it goes. Yeah, you could. It's just going to take a long time. Yep. I'm just saying, after rolling through these problems and going through tests, people were most efficient or able to either interval test it quickly or able to sketch a graph without a doubt. You want to try to avoid that calculator. But if you want to use it, that's fine. So I do f double prime. And second derivative is? Does that factor? Sure, yeah, you can take out negative 4 if you want. You get 3x squared minus 1. What are the solutions to 3x squared minus 1? Well, let's see. 3x squared minus 1 is equal to 0, so 3x squared is equal to 1. So x squared is 1/3. So x is plus or minus the root of 1/3, which is the root of 3 over 3. Well, that's a pain in the butt. Root of 3 over 3 is like 0.57. Again, I don't want to test because I just don't. What shape does that make? Parabola, right? Is it up or upside down? Upside down. Question. Oh, sorry. All right, so negative root of 3 over 3. Root of 3 over 3. So I've got negative, positive, negative, right? All right, show me you're smart. Increasing. When? Good. Decreasing. When? Good. Concave up. When? Concave up. Right. Negative root of 3 over 3 to root of 3 over 3. We'll get to that. Concave down, negative infinity to negative root of 3 over 3, union with root of 3 over 3 to infinity. Okay, so we got max, we got min, we got inflection. So, how do I determine when I have a local max? Do I look at the first derivative test or the second derivative test? First derivative test. Local max happens when the first derivative changes from positive to a negative. When does that happen? Negative 1 and changes from positive to negative at negative 1 and at 1, right? So there's two of them. Local min happens when it changes from, and that's going to be at 0. Okay, so if we want to be able to figure out those y values, what do we do with negative 1 and 1? Plug it into the original. Negative 1 to the fourth is 1. Make it negative. That's a negative 1. And then plus 2 is going to be positive 1. If you plug in 0, you get 0. What do I do about inflection? When does the inflection occur? Inflection occurs where the second derivative changes sign, right? Yep, negative root of 3 over 3 and positive root of 3 over 3. So I plug those in. Negative x to the fourth plus 2x squared. If I go into my table, type in root of 3 divided by 3, I get 0.56, and you'll get the same one over here. Two max, one min, two inflection. Now, you don't have to write this part down, but I want to show you something that I think is pretty cool. So, picture Isaac Newton back in the day, okay, 1600s. He wants to know how to sketch as accurate of a graph as possible of negative x to the fourth plus 2x squared. And he doesn't have a graphic calculator. So how does he do it? Well, he finds some points. What are my local maxes? Negative 1, positive 1, right? And positive 1, positive 1. Local min at 0, 0. Inflection at root of 3 over 3 and 0.57 or 6. So I've got points right about there. And if you were to just factor this, obviously he'd be able to do this. Take out a negative x squared, and you get x squared minus 2. So this is going to cross the x-axis at plus or minus the root of 2. So all of a sudden, he's got some points that he can use to try to generate what he would hope to be a really accurate graph. Jerk, Carter. Y equals. Okay, so window, I'm going to change this to negative 3, positive 3, negative 3, positive 3. I got rid of them for something else. Yeah. I mean, that's perfect. Yeah, I mean, Isaac Newton was able to do a lot of good stuff in a short period of time. Now, you're like, well, no big deal, Mr. Gens. I knew what that one looked like anyways because I'm really smart. Well, good for you. But I bet you don't know what letter C looks like, do you? letter C is going to take some space. Okay? I need to take the derivative. What rule do I use to take this derivative? Quotient rule, derivative of the top. Derivative of the bottom. Times top. All over the bottom square. Let's simplify that. What do you get at the top? Negative 9x squared plus 9. And the denominator, we have x squared plus 1, 20 squared. All right, first derivative, way to go. Now we need to interpret and understand it. We have a fraction. Is the fraction equal to 0 when the top is equal to 0 or when the bottom is equal to 0? Top. What if the bottom is equal to 0? Then it's undefined. So, we do need to look at where the bottom is equal to 0, but that's where we get an undefined value. That's where the derivative does not exist. Now look at the bottom. Can the bottom equal 0? Why? X squared plus 1 is always above the x-axis. It's always positive. It's never going to cross. So we don't really need to even focus on the bottom. We know the bottom is always positive. Let's focus on the top. Negative 9x squared plus 9. Can you solve that? Factor out negative 9 and you get? Okay, what are solutions to that? Do you know what that graph looks like? Right side up or upside down? Upside down. Everybody good to go there? Yes. So therefore, you can tell right away, the function starts out decreasing, then goes to increasing, then goes to decreasing. And you can tell here it has a local max or local min. Local min. Because I go from decreasing to increasing. Right here I have a local max. Very good. So let's find the second derivative. Quotient rule. This gets a little disgusting. Derivative of the top. Negative 18x times the bottom minus what? Minus the top, negative 9x squared plus 9 times the derivative of the bottom. And what rule do I use to find the derivative of the bottom? Chain rule. What's the derivative of the inside? 2x times the derivative of the outside will create a 4x times x squared plus 1 to the first power. All divided by what? What do you want to do now? All right, let's factor the top. What can you take out of the top? What can I take out of negative 18x and negative 4x? A negative 2x. Let's take out the negative 2x. Okay? What can you take out of x squared plus 1 squared and x squared plus 1? X squared plus 1. Looks like we have our common factor. Let's take out our common factor. What are you left with here? 9 times x squared plus 1. And if you take a negative 2x out of the negative 4x, what are you left with? A positive 2x, right? And we have a negative 9x squared plus a 9 still there. All over. Yeah, take out one of the x squared plus 1s. Let's get rid of that. So I've got negative 2x in the numerator times, what am I going to end up with here? I've got a 9x squared and a, wait a minute, not the 2x, just the 2. 9x squared and a negative 18x squared make? Negative 9x squared. Then I have a positive 9 and a positive 18 is going to make I took a negative 2x out of the negative 4x, which should just be 2, not 2x. All divided by x squared plus 1, quantity cubed. Yeah, it is. We are going to do D. We might just want to attach a separate sheet of paper or something. Okay, let's make another right here. So the x squared plus 1 goes away. And then as you look here, 9x squared plus negative 18x squared is a negative 9x squared. Then 9 times 1 is 9, and 2 times 9 is 18. That makes 27. So where is this equal to 0? 0. Where is this equal to 0? Very good. Negative 9x squared plus 27 equals 0. So I've got negative 9x squared equals negative 27. X squared is 3. So I got negative root of 3 and positive root of 3. This is a cubic, right? Up top here. Is a cubic positive or negative? Positive, so it's going to end going up. So negative, positive, negative, positive. So we would then list all of our intervals for increasing and decreasing concavity. We will pick up with that tomorrow. We'll finish example D. You guys are going to have a lot of time to work on an assignment. And we will finish up this lesson on Wednesday in its entirety.